Okay.
Okay.
So,
Hello.
hello. Oh, sorry.
I am Kevin Carlson, and I've been asked a few minutes ago to talk a bit about instances while I'm here visiting Oxford. Um, so I gave a full wide audience talk on this in the Topos Colloquium a few weeks ago, but I'm going to try to target at getting to the most exciting um, bits for and David and Jason here. So let's see how it goes. Okay, so I won't give any of the basic definitions unless somebody begs me and tell me when it's time to slow down. So D is um, a double category. This is all probably going to be coming from the paper of mine and Evan posted end of September now, I guess, on which the title is something like this. So I don't know whether I'll try to keep saying this all the time, but everything that we do in this paper applies either for simple or for Cartesian double theories, mutatis mutandis. And it's one of those things where the simple theory is really not much easier than the Cartesian theory, so that's fun. Um, so we know that a model of Cedric I is seen as a
So this is a strict double category, or
no. Yeah, okay. I guess I think it's a theory, so probably it's strict.
Mhm.
Um, I think that's a bit of a it's a pretty contingent choice whether you think your theories are strict, but yeah, we do say that. Okay, so sure, D will be strict. And models as usual. Ooh, I can hit undo accidentally on the stylus. Um, as usual, models are lax double functors. And you guys both know the definition of a module. Like I don't know how much on the Lambert-Patterson boat you are already.
this is like a loose morphism and double category.
You've
Um,
seen
A module is
oh,
a lax double functor from D times the walking loose
right,
arrow,
right.
And then you slowly compute out what that actually means.
Yeah, exactly.
Is this
So,
like
mhm.
Jason? You want to see it? Let's just see it.
Yeah, yeah. I mean, I'm gonna say it. I was just getting an idea of what's in your heads. So, a module between models X and Y. Right, as David says, the short definition um, uh, is a lax functor um, tap, tap, tap. Nope. Okay, I can only use that on accident.
like
Um, from D cross loose to span, restricting on the endpoints to X and Y. Makes sense? Makes sense as a very packed up definition. So this is right. So these are the loose morphisms in um, the VDC uh, of lax functors D to span. So there's you can vary the codomain there as well and get virtual double categories um, of lax functors, natural transformations, loose morphisms, and something called multimodulations.
right.
There's a close parenthesis there. It is generally virtual. These things generally don't compose like many kinds of profunctors. This is sort of like a dimension up profunctor um, compared to the things that David's usually on about. So what is contained in here? The most important um, data are the components um, for a loose map in D If that is 0 to 1 by L, then the module has these components, which we just call that. And so the main, yeah, that's the most important material. Similarly for cells, which I could write out, but I think I don't need to. There are components that do this funny diagonal shaped thing crossing from f of x to g of y. Also similar components on cells. And so if d is 1, right, then you just have a category at x equals y, and you have a category f of x and a category g of y, and you have a pro arrow between them. And so far we would just have a span between the underlying sets of categories. But then the last main thing is the actions.
Wait a minute.
Yes, I will.
Continue.
Okay, I waited a minute and it worked. So so what are the interesting laxators in M? Would it be appropriate to the style of the seminar for me to allow someone to try to tell me what kinds of interesting laxators there are?
Sure. I'd like to. Yeah, so we've got these maps, f of x, g of y. We probably should have something like if we've got like a loose u from x to x prime to x, then into the domain of M,
Yeah.
then we should have like an fu here, and what maybe a globular cell fx prime m gy. I don't know what we'd call this, m comma u or something.
Exactly. That's one of the two kinds of actions, and these come from, if you like, these look like laxators, right? They're globular, and they are indeed laxators. For instance, for like more precisely, it would be something like u and the identity of 0 composed, or not composed with comma, comma, n and L, as we were seeing there. So those are composable in this product, right, of d cross loose. And so you need a laxator for them, and that gets you actions. So, and similarly on the right.
And so like,
Sorry, go ahead.
oh, I guess we're calling these modules because of like, we take the domain to be a point, and we take, instead of span set, ab or something, then we're genuinely getting modules between rings. The looping, right? Like a lax functor into ab would
Yeah,
be.
which double category of
Oh, okay.
Yeah, that probably works. But I have to think of a second. So you need
You want to get, if you want to
add it. It would have, you have to enrich
ab with
first,
tensor,
right? You
No,
have to.
You just mean the delooping of ab with tensor. You have one object of the
Oh, right.
pieces of groups, and they compose by tensor, and then a lax map from
A point
in there would be a ring, and then
right, yeah,
this would be a biological.
Right. So in that case, a lax functor basically, a lax functor, right, constructs a ring, and then is in
Although I
modules.
guess you want, and then the type morphisms you want are. I guess you don't have any type morphisms.
So far, I don't.
The squares are the homomorphisms. Right?
Yeah. So this is the usual.
This would be the virtual double category of that, which is that's cool.
Yeah, this is the usual delooping of a monoidal category into a double category as a fully horizontal monoidal or multi.
Right.
Well, not multi unless you're virtual.
Can we see an example of this for some kind of I want to say simple, but not in the technical sense. Simple double theory.
Yeah.
Like, let's say I could, you know.
So the examples I did in my colloquium talk are Luce itself and the theory for multi-categories in the Cartesian case.
Categories.
Uh-huh.
I know that's more complicated, but like that would be that would be really an interesting running example for me.
Yeah. So let's recall a theory for multi-categories. Um, uh,
This is really internal.
yeah, no, I was considering whether to comment about my wonderful lunch we all just enjoyed.
That we all enjoyed, for the record.
So the theory of multi-categories, maybe let it give it a name. Mult is generated by an object and a pro arrow mu n for each n. And by saying unique there, I think I actually am done with the definition because I've included the associativity.
Sorry, so is this a Cartesian?
This is going to be Cartesian, yeah.
And the point for Cartesian is it's just gonna pass everything, any structure that appears on the product has to be the product of the appropriate structures, and we just kind of ignore.
Yeah. So you when you're being careful, you check some little lemmas that say like a functor is uniquely determined by its action on things that are, especially because this all the producty stuff is freely generated in here. So it not only is determined by, but also conversely something is full.
Okay.
Yeah. So should I say for a sec why this is why this theory is correct? It's not the most normal definition of multi-category.
Right. The analogy is that to like the theory for categories as a single point, and we just got the identity, and so we're extending that to like mu.
Yeah. So right. So what are these mu n's? A model sends x to to the category of unary arrows. Let me call it so it's slightly unusual because definitions of multi-categories don't usually start with a category of unary arrows, but it's more natural for certain formulations. And then mu n. So I'm saying to the category because we know the general theorem that Lax functor into span is the same as a normal Lax functor into prof, right? So to see what all is really there, it's sometimes easier to say things that way. So this goes to a profunctor then, if you like that. What do I call that? So the basic point here is that you can describe a multi-category by giving for every n a profunctor of n-ary arrows from n copies of the base category to one copy, which just says that, well, certainly you have such a span, and in fact unary arrows act on both sides of n-ary arrows. Laxators give you compositions and blah, blah, blah.
Right.
That basically help.
So if in these cases where we just got D as a point, this is just the like the mod. This is what's referred to as mod of a virtual double category, is that right?
Yes. Yeah. Mod of a virtual double category is the virtual double category of Lax functors from the point.
It's mod of span, right? Yeah, in this case.
Because
you're mapping into.
If you're mapping into span from the point, then you'll be a mod of span.
Prof or whatever. Is that what?
Is prof, right? Mod of span is prof. Yeah.
And that's another, which if you call that bimodules, we'll be like, oh yeah, I get it.
Yeah, right. I was surprised you asked. It's a nice example, but I was surprised initially you were asking about ab rather than just saying like, ah, well, if D is a point and the codomain is span,
Mhm,
then a
mhm.
module is a profunctor, which Australians sometimes call modules.
No.
So, certain Australians, I mean.
It should really be like a bimodule or
Yeah. There's some ideology of saying module
Right, yeah,
instead of bimodule, and yeah. So that's a model of multi-category. So then, what will yeah. So okay. So right. So I had to think what actually is going to happen here. What actually happens when you look for a module between two multi-categories, you get something reasonably messy. So hopefully we'll at least
Okay, so
communicate why it's a
right.
little bit messy.
Can I try doing it?
You sure? Do you want to actually
Did I write it?
write?
All right.
Yeah. This is fun.
mean,
The
you
two
can-
tablet thing is a cute idea.
Okay.
So the top button is eraser if you need to erase
This
things.
down, or maybe I'm like down here. Oh, I have to go. Okay. Oh, this is like math in this.
Yeah.
Okay. So I'm down here, and I'm like, so I have, you know, f of x, and I have g of x, and I give one of these. Oh, for any m, right? So this is an n, and then I have I have m of mu n. And that's acted upon this. So this is going to be the right kind of bimodule between multi-categories, where I think of this as being, I have a vector x1 dot 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 x, and these should be really small x's, like because they live in little x semicolon y. And it's acted upon by, so if I think of like, if I write it like this, here's a string diagrammatic presentation. I write it like this.
Yeah.
Where this is m, and then I have in here, or maybe I'll put like, this is like a box or something, right? This is my module. It has an m on top, this is super module. And then over here, I can put things for, this is gonna be the left action. I can put things for, from f, and then here, I can put things for, this is cool.
Yeah.
And then
Another
here's where I
M.
can put things for you. And this is nice. Right.
Yeah,
But,
I would have
yeah.
drawn this picture something like
This is M, and this is
like, great, here's some multimorphisms on the left from coming from F, and then there's like a, well, yeah, okay, so David's trying to draw the whole thing. But so for the left action, you have something like that composing a squiggly guy, a multi-heteromorphism with some multimorphisms from F on the left. And then you can do a similar thing on the right, where you compose several multi-heteromorphisms with a single multimorphism from G on the right. And
So are we describing like the laxative?
so these, yeah, what are these things are the actions.
Right.
From the third thing I named it there. It's kind of funny that I can't cause the scroll to occur.
Oh, right. Yeah.
Like
I
the
know.
actions. I love them. But yeah, so those are laxators.
cool.
So that's cool. But now great. So
Sorry, just to be,
Yeah,
the
yeah.
laxatives say that I can like, if I've got we're using boxes for M, are we? If I've got some, I mean, there's like of two sorts. One is if I've got like a G here, I can pull this.
You can right act on it.
Right. Okay.
So that you put that if you want,
Right.
the composite lives in a big box. Yeah. big
Right. And
box.
this is indexed by like, okay.
Yeah.
Right. And similarly, if I've got a bunch of Fs on the other side, they get absorbed into the M
Yeah.
Okay.
Mhm.
And this is cool because certainly if you take terminal on the left, this is what's normally called an algebra for the multi-category.
I do not think so.
No?
No. So yeah, that's exactly what I was going to go ask next. So then, because what is the?
Oh, because it has n many dots.
Stop interrupting. Maybe somebody's trying to listen, David.
Sorry.
Stop figuring out the whole talk in real time.
Sorry,
Yes,
that's
yeah. So the topic of this talk is really about instances and coinstances which should be the thing that happens when you take modules into or out of the terminal model. So what if f is terminal, a module from 1 from 1 to G, a multi-category G.
Is this in the multi-category case in particular, or?
Yeah, I'm still in the multi-category example. Example. Shoot.
So yeah, when we have up there, we have f prime is terminal. Sorry, f is terminal.
Right, yeah.
And then so
And,
right.
Right, and in the category case, this would just be like pre-sheaves.
This, yeah, in the category case, this would be
co-pre-sheaves by how I like to vary things. Yeah, right. So yes, so you can recover pre-sheaves and co-pre-sheaves by modules in and out of one for categories, and so
I think that I generalize the
but it turns out, as we see right here, and you can also see the failure in a more elementary way in Luce itself in the theory of a profunctor. It's not true. It's not true for theories that have interesting pro-arrows in the theory that a module out of one is the thing you want to call an instance. And so in particular, if you try to take a module out of one into a multi-category, then you get, right, what's the thing you're thinking in your head? You want, probably, a useful thing to recover is you want a multifunctor from G to set, which involves, for each object, a set, right? But a module out of one involves for each object countably many sets of kind of n-ary heteromorphisms into that object for every n. And then you have a complicated lattice work of actions for varying those n's. Even though a dot is just a dot, there are many trees made out of dots that are.
So if I had if I can trying to just work with the unary one, whatever. The problem is that when I act on it from an n-ary one, I put n of them together and I get an n-ary one. I got one in the form like with dots there. So I just like end up with more commas.
Right. So you do not get any action of G on the unaries. That's exactly right.
But there's nothing in here. But when we compose them on the right, like we end up unioning. You end up with many more arities on the back, right?
Sorry.
So if you acted, you could draw things in such a guy as heteromorphisms with no domain.
Well, but okay. So there's one.
Right, and if you acted on a few of them, just to finish the thing that David was pointing out, you get a ternary guy into G naught. So I think what David was pointing out is there's no obvious way to pull a multifunctor into set out of this data, which we will now repair in a moment. Cool. There was another thing you were gonna say.
Yeah, I was gonna say, like, what if we took not the terminal one, but like the subterminal one with only unary morphisms or something? But that's not the problem here.
Yeah.
The problem is not the left section of this. It's actually just the type signature.
Yeah. So
the morphisms in the loose morphisms in the theory itself, the domain.
Yeah.
They're just
right. So that's a very good point. And it would not quite work. What the difference between using one and the walking ob multi-category here is
I can decide that some of my things
you have interesting ways of acting on the left, basically, in this case. And actually,
sorry, what's ob?
M is ob is so one is the terminal multi-category, which is one object and one multimorphism of each arity.
Yeah.
Ob is the walking object, which has just an object and an identity.
Right, one unary morphism and no.
no higher morphisms.
Okay.
Because not every object in a multi-category can be picked out by a map from one. Maps from one are monoids, not just objects.
Right.
Sorry, not every.
It's-
Sorry, what was that? Not
If
every.
you have a multi-category,
Mhm.
yeah, and you want to pick out an object.
Oh, it's not the same as a map for the terminal
Right,
multi-category.
right.
Okay.
Right. Maps from the terminal multi-category are monoid objects. So what actually happens here, this is just cute, and nobody else likes this, so I'm hoping you will, is that M is a multifunctor G2 delta plus set. It's a multifunctor in augmented simplicial sets. So you get those. You can see the n simplices for every n, and you would still get an n graded if you used ob instead of one. You would get a multifunctor G into n graded sets.
Into
But
what's
that,
graded? Set? N
into
graded.
Oh, yeah,
bold
yeah.
n graded.
Oh, okay, just the list of.
Yeah, you would just have the n area for every
Right, because you can replace you can either delete something on the back by composing with the nullary,
Mhm.
or you can split it into multiple things, but you're always preserving order,
Yeah.
and those together generate together with the nullary, the augmented simplex category.
Mhm.
Beautiful. Wow. Weird.
Sorry, can I just to make sure I've understood? First of all, we're talking about modules between Cartesian
Yeah.
functors. Is there some Cartesianist property that we also need to impose?
Yes, you need the components to respect products. And so I'm basically, David hinted at this earlier, I'm basically implicitly doing that by only thinking about the generating
The map center.
the loose arrows in the theory that generate under products.
Right, okay.
Because there are also some more loose arrows here that we've never mentioned. Like there are arrows from x to the m to the x to the m.
Right, but they all come from.
They're all
that
products of.
entity. Okay.
So yeah, that's a good point for being
Okay.
careful.
And so here, you're telling me that modules from the terminal multi-category don't correspond to multi-functors from G into set. They correspond to these things.
Into augmented simplicial sets.
Okay. And if I looked at the object multi-category, I'd get these things. And can I see, so for each like G, I guess I can look at n-ary maps from like n copies of from the terminal thing
point, yeah.
into it. Is this somehow giving me, okay, for my G, I get for each ordinal n or finite ordinal, I get the set of
right
those things?
Yeah,
Is
that's
that-
how you get your augmented simplicial set for each, or that's how you get your n-graded set.
Right.
Yeah, and then to get the augmented simplicial set, you act by the various multimorphisms in one.
Right.
Pre-composed. by
Right.
things.
This would be like an
Yeah.
active or
Yeah.
right.
Yeah, and then
Okay.
but you also have the
I've got the nullary
pre-composition,
one, right.
And that
And that
that's
just
that's how you
removes.
split them out. So that's
Okay. They're generated by like the binary
so that gives you
binary, the empty area.
injections and surjections, I think.
Right, okay. Okay, that's cool. Okay, I think
Yeah. So that's just the exact answer to what modules out of one are is just kind of a cute.
That is cute. It's actually less scary somehow.
Yeah. It's not just some absolute chaos, but it is
it's not.
considerably more than you probably want.
Yeah.
So how do we recover what we want? Well, let me tell you. Let's stop the example for a second.
What do you want?
Right, I want multifunctors from G to set, right,
Yeah.
which is G algebras.
Yeah.
So how to
Leptonic spend or whatever.
God knows, probably, yeah. How to I want something to, as elementary as possible, and double categorical as possible. So how to get rid of the one is acting on the left of this module one is providing a lot of data into this module and also is acting on the left in a highly non-trivial way. And it turns out we can fix all of that at once. We usually don't want one to act interesting. So let's make it stop. So in general theory D, given a module 1, 2, x, and so this is all about action. So it's all about composable pairs of loose arrows in the theory, which is why this problem only comes up when you have non-trivial loose arrows in the theory. One of these could be identity, but they can't both be identity. So you get two different things from the actions. You have a fully lax square.
Sorry, what?
Yeah.
X, M, and N are composable looses in which?
In D, sorry.
Oh, okay.
So these are all ones. These are all ones. Blah blah blah. This is M N, which goes to X Z. This is
So the thing we observed above was for a very specific D, right? So this is the same D?
No, this is
This is for anything, but we could.
Okay.
I'm not talking about an arbitrary D that happens to have some composable pair in it.
Okay, it's not like a Cartesian.
It's not. Yeah, no. Right now, it doesn't need to be Cartesian.
Okay.
But it's not so different. If
It's the same. The difference. So a Cartesian module between Cartesian models has some product preserving property. An instance is going to be a module with some special property, and you just give both special properties to get a Cartesian instance.
Right. But so there's some issue, which is the interesting action of one, and it manifests in like for general
manifests
D.
in simple double theories as well. Yeah, I on David's request, I jumped straight to Cartesian.
Okay.
But so you could imagine if you squint enough, the simplest case where this happens is when D is the walking loose arrow. So its models are profunctors.
Right.
And with that example, I'd be trying to basically recover attrits. And so you could see already here what happens is that the problem is this action in the upper right triangle, even though one is trivial as far as how it relates to M, it's not trivial as far as how it relates to M and N together. That's where you get this non-trivial action of one that we saw in those multifunctors into augmented special sets. And so all you have to do is make that be ISO. So an instance, the packed definition of an instance.
So you're trying to get into, instead of being a
call these lambda.
You're doing this thing where, like, instead of being a bimodule, you want something more like a lax transformation.
Maybe. Well, but I'm only getting rid of one of the actions.
Yeah. That's how you would make.
Yeah, I guess.
Like,
yeah, I see what you mean, because it's like it goes all the way across.
If you pretended that was well, now you have a single cell filling it. If you pretended this was an equality, it would be a single cell.
Yeah. Right, and I do, and just pretend it's an equality. So the model could be Cartesian or not, as we've been saying.
I don't remember.
Whatever. Yeah, that's impossible. No one has ever known that. As a module into D from the terminal model, such that all the and I really just define it in the strict way. It's not, there's a coherence theorem. You can get rid of it, but this makes a reduction to an elementary definition of an instance much easier. So if you make all those things invertible, then you recover good things, and we can explain this if you want, but an instance of a multi-category recovers the desired thing.
Right. So if we just look at the case where D is a point, do we get something?
Yeah, so for the point, you have no, you have, if D is the point, then the only composable pair is identity, identity. And so here you have the terminal category, and here you have some set over some other, the objects of some other category.
Yeah.
And you have an action cell here, and that should be
Right.
thing that I am having board brain a little bit. I think that M lambda is automatically an isomorphism in the case of D. So let's see.
I think I've like in the abelian case, this corresponds to like your bimodule being like free on the left or something, or on the right. If we just look at an arbitrary module between like rings.
Yeah, I haven't actually thought about this case in like 7 months because I just thought it was straight and pinned it down. But yeah, so now it looks like, right. So, right, if M and N are both identities of the only object in the terminal double theory, then N equals M composed with N. And so these are both the same set over the objects of X. And you have this right action of the category of X on that set. And then you have, I guess this says that you could have an extra endomorphism of that.
Right. So these are profunctors then, right? We've got like some profunctor P, one P to C, and this is the identity profunctor. And maybe this is just right. Okay, so if this was something other than one, like some Y,
right, then there would be an action.
Then there would be something interesting to say about P. But in this case, it does seem like it's automatically true in the case where we've got no non-identity morphisms.
Yeah, it is. It's definitely automatically true because these modules 1 to X will actually be profunctors 1 to X, which we know are just X sets in the case of prof. So I guess to get that clear of why exactly you want to look at what exactly M lambda consists of in that case. And so that is a map of spans. I'm a little confused right now. And
so right. So this case does, in the case where we've just got a point, it does seem trivial. But if we take a single loose morphism, then each object here is a okay. Then we've got like, we can look at this picture for, I don't know, N being that loose. Is that going to be interesting?
What are you trying to?
I'm trying to, I guess, understand like what constraint that's really.
What constraint that makes? Yeah, I mean, so to see what inverting M lambda does for you. I mean, we could think about the multi-category case.
Right.
Yeah.
I mean, I think it like what it does is it makes this a lax transformation between lax things, right?
Yeah.
So it shouldn't do anything else but that, right? Like, up to ISO, right? Up to like renaming, relabeling. If we ignore those things, then it should be what you would get if you just wrote down a lax transformation between lax functors. Right? Which is not a terribly easy thing to write down, but
yeah.
Right, but I don't
probably
even.
the right way to write it down at all anyway.
Yeah, right.
But like,
but I guess I just what is a lax transformation between these lax functors in the case when D is a single loose and we're going into span set?
If D is just the walking loose,
Yeah.
yeah. If D is the walking loose arrow,
then any lax functor from that interspan set determines a profunctor between categories. The map 1 picks out what the identity profunctor on the terminal category. And then a module is given by
a module is really just a square like that. So a module is.
I mean, it's given by like 3 profunctors.
Yeah, so we were squinting for a minute about what happens with categories. I think there's a unitality of the actions condition that tells you that this M lambda is trivial in the case of categories. That's why I was. Yeah. But so that goes away now in this case, if you've got a module.
The three arrows you're talking about are the one that's associated to 0, the one that's associated to 1, and the one that's associated to L.
Yeah.
Right.
The only 3
The three.
loose. Yeah.
Right.
But then
isn't this
we
always
know that the one associated to L and the one associated to 1 are actually isomorphic.
You mean if we add the instance condition or?
Yeah, with the instance.
Yeah. So a module on its own
seems like
looks like that,
Yeah.
and so you get this weird. So this is a profunctor with coprecives over the domain and codomain categories. An action from this composite to this one, but also this weird endomorphism of the right hand coprecief that nobody asked for.
Not an endomorphism, right? It's a map. You have 3 different ones.
But didn't I do the composable? I'm drawing a square for a single composable pair here, right?
This is a single composable.
Yeah. There's 2 composable pairs.
And then you do this again on the other side.
Yeah. So that you would also have.
Right. I see. This is the left and right side of the.
Right, for a particular pair of composables, and you can do ID then L or L then ID.
Right. So I see. The weird thing here is you end up with this extra. Endomorphism of ML.
Is this always going to be invertible when you've got an ID up? No.
That's the point, right? In this case, like if you imagine just like in the multi-category one, right? Like you can pre-compose, right? Is that true? Actually, wait, hold on a second.
Yeah.
That one, isn't that right?
Isn't what right?
Doesn't that have to be invertible?
Which one? Which one?
We're acting on. No. It's only it becomes the identity when you pre-compose by the uniter.
The uniter here.
Yeah.
But isn't the uniter
equal to that?
Yeah,
for the terminal one. So maybe it is.
The uniters for identities are invertible. Right.
No.
Right. If it's a lax functor.
This is terminal. This is a
but that's terminal, so it is, yeah.
So it is true there. It is true that the terminal one sends it to the identity.
Okay.
But in general.
Oh, right,
the
right, yeah,
actual, like,
Right, right.
Okay.
So you're saying we're concluding that we think that this triangle already is the identity in this case
that
because of the
triangle is
invertibility of
the
this
identity,
unit.
because when I precompose it by the identity, I get the identity.
Right. And now when you look over
And then
here,
that's why,
But
like,
that's not a problem.
if D is the point, then this condition is
right, why
Vectors.
instances are the same as
Other
modules out of one.
side.
Now on the other side, this is not the
On the other
available
side, we have,
uniter.
yeah, this is where we get this extra
yeah,
inclusion, right?
Yes.
And this is not gonna go away,
yeah, this one will not go away until you turn it in.
because that's now a 1L over there.
Yeah, so there's no uniter available.
Well, yeah, which is not it, which doesn't have this unity extra thing. It's just one, it happens to be the identity, so, you know, of one. So in other words, you get this, you have, you end up with three things.
Yeah,
Right,
so
right,
you have,
one.
so you
the right
have,
action on both of them,
mhm.
right? But then you also have this extra inclusion.
Yeah.
And you're like,
Yeah,
oh, what?
well, and it's not, I don't think, it's not necessarily an inclusion, right? You're saying a
Or not
MID
inclusion,
one,
but a
but this extra map. Yeah, you have this extra mystery map from MID1 to ML, which nobody asked for. Right, and
And
so
you just say,
precisely what happens when you get an instance is you just crush exactly that triangle that you've marked 3.
right.
And so now you just have the Coprix sheaf ML on X1 and the Coprix sheaf MN0 on X0, and you have this action, and you have this action.
Or, so yeah, you could think of this as being like, I don't know whether it's more or less right to think of it this way, but you could think of it as there only being M0 and M1 now. And it's 0. and
Yeah,
M1, and
that's,
M1
I think that's
big.
probably, no, that absolutely is more natural.
And
And
then, like, does that, when I say
and
more
in
natural, is that
fact,
general?
yeah, and in fact, there's an unpacked definition of an instance.
sorry, what was
Yeah.
the
I'm
point?
sorry, you have an isomorphism now up there, right?
Yeah.
And you could just quote unquote contract it onto either side. You could,
Right.
you could replace, you could rearrange it so that everything was just written in terms of ML, or everything was written in terms of MN1.
Okay.
And
so,
I'm saying, I was wondering which one is the one you want to do in general, because it would be very nice if you could say like, oh, I'm just gonna like, all of my loose ones, I'm gonna replace with the one for an object
I
of the
see.
domain or whatever.
right.
And then you,
So you can
Yeah.
give the data of a module of this sort just by giving this on objects.
Yeah.
Right, because any other morphism in right,
into
okay.
them is gonna get replaced by it of this way, right?
Right, okay. And that's
Yeah.
like with Lex transformations, right? You only define components on
Oh, yeah,
objects,
yeah,
whereas
right,
modules.
right.
Uh,
Right, that's a good point. Yeah. Cool, and so now what you have here, a module, an instance, excuse me, of the theory of bimodules, which is loose, right? Is going to be a pair of bimodules. Sorry, a pair of Coprix sheaves acted on by, or like right modules acted on by the categories, each of which admits an action by the module left and right.
right.
Or just like, sorry. Yeah, that is, that you get a, you get a map, you get this action, which is like M0 and my original bimodule into M1.
M0 my original, but oh right, the
No,
M.
I'm sorry, I'm doing this wrong.
Okay.
Yeah, wait, no, yeah, it's M0, my
Yeah.
bimodule, M1.
Oh yeah.
And then M1
By
my, oh no, this is just
This thing
is
is here.
it's the right module.
right. So
Right.
there's, if I like compose these,
Yeah.
well rather X L, this is the okay, into M. So this thing is now M. The point is that that MID1.
Yeah.
Sorry, this is wrong, right?
ID1 after
1
1L.
after 1L.
But 1L is identity of 1.
1L is
this
identity.
case, yeah.
Oh, okay.
So
okay.
that's why we're like cheating
Oh.
a little extra bit, yeah.
Oh, okay. So M.
It is not generally going to be the case that you could replace this by objects. Maybe it is, but maybe it isn't.
If you
one-
consider a like left
Legit.
trivial module
Yeah.
but
lack
with
of
something other than
information.
one,
Yeah.
I don't think you'll be able to cut that down to objects, but I haven't really thought about it.
I feel like the intuition that
Hmm.
the cutting this down makes it the same thing as a lax transformation suggests that you should be able to do that,
Yeah.
but it's not totally obvious.
Yeah, well, so I hadn't really been thinking of those terms. So maybe you want to look at this unpacked definition.
Yeah,
That is
yeah.
the unpacked definition we've been using, and we can think how that compares
scroll back
this
a bit?
this line.
Okay.
We can do a little scroll. Yeah.
Um,
So indeed, if you follow through this idea you were just having, David, you can unpack an instance so that all the data you need is the thing. And the point is that this is the same data which for a module you needed one of these for every m, not for every d, for every loop morphism, not for every m.
So this is really, you've really actually cut
Yeah,
down.
it's dropped it down a dimension. But it's not, it doesn't, well, so for one thing, there's the f's and you have to think about that. But
Yeah.
it doesn't seem like it's quite the same thing with the actions. I don't think it's the same thing as a lax transformation between lax functors. Even if everything were just a bicategory, it's not really the same thing.
Yeah, well, from one, I think this is.
Oh, from one, right? Yeah,
But
from one.
The question is whether it
yeah.
remains so if you
Even-
have a general one, but I think it's in general.
I mean,
it is.
yeah, you're giving extra data, right? Like you're giving a specific like diagonal, but it seems like at the very least you should be able to recover a lax transformation just by gluing this with the inverse of this, and then you
Yeah, yeah. I think also I've seen analysis of the combinatorics of lax transformations in the higher category world that use this exact idea. You give a notion of lax morphism, you multiply by the sim1 simplex that's multiplied by loose, which gives you modules, but then you mark things. You do it in this like marked higher category thing, marked world, convolutional kind of world. Where so that you mark all those top ones as equivalences. Of course, that doesn't, make them, you mark them as equivalences, and then when you map into something that is saturated, you then are saying that I've been searching on Google to see where I read this, but I haven't found it.
But it sounds very
for
plausible.
double categories, of course, right? But it's the same idea.
Yeah, that sounds really plausible.
It's nice.
There's I think you can define modules as lax transformations from the twisted arrow category of your like if you've got F and G, then I think you can do something like look at lax transformations like this, and they go
transformations like
sorry, lax.
I'm sorry. What?
Are you saying lex or lax?
Lax transformations from F to G. Sorry, what are you showing us here?
Oh, modules.
These are supposed to be
certain like
modules?
lax
A module
transformations.
is a lax transformation on the twisted arrow
Yeah,
category. Of the
and if you
super-
mark like certain of these morphisms, like maybe there's going to be two sort of canonical morphisms from identities on objects into a morphism into it, and if you mark one of these
I see.
and
Then
ask
you're
that
just
as being
getting-
pseudo on that
Yeah.
component.
Yeah. I think that this does relate to sorry, that's just sent me a message. I think it was the squares construction thing. This was someone constructed the squares construction in higher category theory, and they defined it in this way.
Yeah, well, sure. I'd love to hear.
Yeah,
that.
sorry, I think we're missing that.
Yeah, so that's what an instance is.
We haven't really talked about these. I haven't really thought about this coherence for type transformations, but I guess that's part of that.
You mean
sorry, type.
the fact that there's structure for type morphisms?
Yeah.
Yeah,
Okay.
it's like, yeah. So if you had, you might think about the D being the walking tight arrow,
Mhm.
so that a model is just a functor, XD to XD prime is just a
Okay,
functor.
right.
And then you have a Cauchy on each of those categories, HG and HG prime.
Mm-hmm.
And then F just gets sent to a functor of the categories of elements of those Cauchys over their bases, or you could say a functor from the pullback from the first one to the pullback of the second one, or from the left con extension of the first one into the second one. It's a morphism in the category of elements of the fibration of pre-sheaf categories. I don't know. I thought that was going to help, but then it was long.
Mm-hmm.
Yeah.
Okay.
Yeah.
Okay. So an instance is the same thing as a module in the case where D is a point. So those examples are sort of
Right. D being a,
interesting.
yeah, and if D is wholly tight at all, if there's nothing, if there are no
Right.
loose errors in D, then instances and modules from one are going to be the same.
Right. Okay.
It's only once you start to get loose errors that it gets interesting.
Right. Okay. And so in multi categories, this do we observe that instances from the point give the right notion of multifunctor?
Yes, we will find that. Were you wanting to find that together, or
Oh,
can you
yes,
just
yeah.
confirming?
Yes, I'd like to see how that.
Yeah. So
What we.
my car is mad at me. It wants me to come home. Yeah, so let's see that. Just deciding where to put it. So for a multi-category, maybe can I just apply the unpacked definition and you believe me that the unpacking process works rather than
Sure.
going back up to the
Oh, right, yeah. It's a question
more
whether
direct
we
definition.
accept that this comes from.
Yeah.
Yeah.
Yeah, but it's sort of believable that something's gonna happen.
Mhm.
I think something like we can sort of take that.
Yeah.
So for a multi-category, I guess we're calling it G. So to go back to that, an instance in the unpacked definition is again, you only need to give it's going to preserve products. So you only need to give the main thing that happens is that you only need to give this span from of unary heteromorphisms from one to the objects of G. The type, there's no type maps. And then for every n, you need h of mu n. So the reason you only have to give hx and not hx to the n for every n is the preservation of products. Remember, for a module from one, we were giving h mu to the n at this level, but everything shifted down. So now we have actions for every n, which look like 1, 2. Could be written in either direction. This is actually, I really like this diagram because we were trying to draw those string diagrams of these actions and they're kind of enormous. But here we go like this. And I, nope, I get an action. Like this, which is hx. So this says that if I have an n-ary morphism in G, and I have a bunch of
So each of these HX, this HX is like a family of
Yeah, so I'm
Objects.
drawing loose arrows in span, so right, so
Yeah.
HX is a set over the set of objects of G.
right.
Or a co-presheaf on the category of objects of G, if you like.
Mhm.
And then the actions say that if I have n hetero elements, I'm not sure what to call them when they're unary hetero elements over n objects of G, and I have an n-ary morphism out of those n objects, then I can act to get down to just one unary guy like that. Which is the kind of action we were looking for with the module before that we couldn't
Right.
have.
So like what you've asked for here is that the pre-composition maps by the terminal thing, which we're like re-irradiating. You've asked that these be an isomorphism.
Yeah, and so
and
right. So
therefore-
as a module, this would really map to a quaternary.
Yeah, but
Thing
then
over
you map,
G.
then you re-isomorph back. Yeah.
But
Exactly.
because the left action is invertible,
Yeah.
there's a unique unary guy under that quaternary. And so I can essentially just think about my action as giving me back a unary, which is the behavior that you want for a multifunctor from G to set.
Yeah. Okay. So
Hmm.
I've heard that you had a Grothin deconstruction for these.
I do.
I would like to see that.
Yes. Okay, great. And we finished one page. Perfect. Okay, the grounding construction.
Right.
Have you looked at these where the domain is not the terminal one, by the way?
No, I haven't thought about that, and that's this, yeah, lacks because the paper then goes in this direction of the
Right,
grounding
right.
construction. That's right.
Yeah, kind of just curious.
Yeah, it's a really helpful thought. I'm glad you know one.
Anyway.
Okay, so given your model X and an instance of it, we're going to have Gordon construction, and most of the actual construction will, I mean, you would guess it if you try to do it. Do you want to scroll back up actually to the unpack definition? So right, so you got an instance. Okay, what is H of D going to be? It's going to be H of D. What is H of F going to be? It's going to be H of F.
Well, just can I say that again, but slow,
Yeah,
in
yeah,
the sense that
yeah.
these are spans. These
Yeah.
are spans.
Yeah.
So in fact, above X of D, I actually have H of D a set with
Yeah.
a map down to H of D.
Yeah.
So I just take that out of being a span and crank it up to being an object and
Right,
a
right,
polymorphism
right,
down.
right.
And
Yeah, so it's pretty.
Yeah,
It's
for everything, it gives me a whole new lax double functor.
yeah.
which is
So
pretty cool.
it's the kind of thing that there's a number of things to check, and it takes a little while. You know, I haven't said about the coherence conditions for cells and stuff like that. There's a a number of pages of checking that this actually works.
Imagine that.
But it works, and basically the way that you started guessing.
What are we doing?
Sorry, I'm just maybe.
So maybe let me see if I can just go. So I did that for the object,
Mhm.
right? I say, well, the object was a span from one, which is just a map over it. So I take in other words, the Grothin construction, I take HD, the set, to be the value of D at the Grothin, right?
Yeah.
And
You were
then
just
I
copying the unpack definition,
Yeah.
so we have it here, Jason, so we probably don't need this stuff.
Yeah.
Mhm.
So for a type map, I already have my type map there because I know what a morphism of
Mhm.
spans looks like. And then for a loose map, I have my thing, and I have a span, and I have a map into this other thing.
Do you want to draw?
I don't. Yeah, let's.
So let's
You
do
have you
that.
followed along?
No, I'm not.
Let me do this then.
Yeah.
I'll do it out, but I'm
Yeah, okay,
stuck
go,
on
you
that
go,
one.
ahead, yeah.
All right.
I was gonna start writing, but you go ahead.
And then and then you'll walk me through
And write it
the,
in terms of integral age.
right. So if I call this like 1, 2, 3, let's say, I'll go 1,
So one is actually, we have HD. Right, I'm just writing out what it means to be a broken arrow in span,
Mhm.
XD, right?
Yeah.
Mhm.
So we just consider this as HD over XD.
Yeah, and so
That's
you could
our-
write,
so
you could
that-
write
it's
integral
like
HD
integral.
equals HD, yeah.
Equals HD.
Mhm.
Mhm.
And then two, well, like what was two here? We had a map like this. We had HD prime. We had XD prime. Wow, I find it very hard to write in this. We have this simple one, and then we have this map here, right, which was HF. That's just what is down here.
Mhm.
That's just what it means to be that.
Yeah.
So you can see
So we
that
get
we
a
already
type
actually
map.
have
Yeah.
the type map.
And you
we
build
need.
it, and you're building,
And this means that this is natural.
right, so you're building integral H to the lax functor together with a strict natural transformation into X simultaneously.
Right. So, right. And then three, I'll let you
3,
walk me through.
yeah, this is the cute part. So we have some M loose map in D, and we need HM a loose map HD to HD prime.
Is it
which will be a span, yeah, if you like. You can do a lot of this anywhere, in any codomain. But so what we have, I think so. I'm sort of muttering and thinking at the same time, so don't take me too seriously. So what we have is this cell. You know what? I immediately take that back. I don't think it's true. And let's see. We want so let's draw this cell HM out in more detail in span. So we had this HD down to XD from XM, and I'm naming the apex of a span the same thing as I named the span.
Okay, so we're writing out what's in 3 on the right over there.
That's right.
And we have a map from
And
the
I also
pullback
have
of that
Mhm.
thing there,
this,
all the way down to the, yeah.
like so. And oh golly, would you look at it? I needed a span from HD to HD prime.
Mm.
Oh, it's that one.
Yeah, that is it. That's HM.
Whoa.
Ain't that cool? And then, yeah, you draw a bunch of really big quiver
And then,
diagrams.
wait, hold on a second. The
to
map down to
things.
XD is so twisty in here, but the map down to XD is, I already have that match from HM to XF. It's right there. That
Yeah,
right leg.
Yeah.
And then my,
Yeah, a lot-
and
So-
then the
right,
rest
so-
of it commutes is like just somehow in here.
Yeah, if you
Like,
turn your head in
Right.
the appropriate
really
way, you'll see that you have a map of spans HM
Cool.
to XM.
Cool.
Yeah.
Right, so it's a thing we're taking,
That's
okay.
way easier
down
than
in
I
here.
had.
There's nothing legitimately hard about it. There are, as
And
I
then you have to
said,
check
some things
everything. I know,
some things to
okay,
check,
that-
but it's very, this stuff is really very crank turning.
Not easy, but straightforward.
Yeah, everything happens where it should, but it's nice enough that there's those moments like that where you're like, I wasn't really sure that was going to work, and then it
And
worked.
then it works.
So cool
This is
when
very nice.
math is true. Yeah.
This is very.
And right, and so so then you're like, okay, great, I can turn an instance into a model over X, and then you go like, all right, which models over X have I gotten here? Well, in any model over X, you would have, if K maybe is any model over X, you would always have these span maps.
You're gonna make one of these squares a pullback, aren't you?
And I'm going to make one of these squares a pullback. We have,
Cool.
as you can see here, if you squint appropriately, we have made exactly all of these squares a pullback in our construction of the integral of H over here.
Yeah.
Sorry, what's K?
So K is now, I'm
Yeah,
trying to
by
say, yeah,
definition.
I'm trying to say what kind of model over X have I produced here? So
Oh,
now
okay.
if K
So
is anything
KM
over
is
X.
HM as we've constructed.
Yeah,
Right,
if K is any model over X, then I have these things. And then so I know already by construction that integral of H makes all of these squares pullbacks. Because this square is this square.
Integral of H makes all of these pull. Right, okay, so sorry, we're meant to be looking at this diagram on the bottom left and seeing that we've got this special.
Not really in the
Oh.
bottom left. Yeah, there's a little
Oh, okay,
it's,
so
it's a little twisty.
It's
Yeah,
nifty, but it's
because of the
like-
ones. The ones aren't there
This-
anymore when you're in models over X.
This would have been HM.
Right.
It would have been this thing.
This,
And so this map
this
here
square here is
is that.
right, okay.
And then this map here is that.
Yeah, okay.
And so it is a pullback.
Okay, okay.
And so then the theorem is that
Wow.
integral, I haven't said what a morphism of instances is, but it's just a modulation of model. Oh
Okay,
yeah, I
so
was gonna stay there.
Is this like a Cartesianness condition or something? So
This is exactly what it is. Sorry, if you do this for the point, this is exactly the like definition of discrete observation for internal categories.
Right,
Which
so
is
like-
kind of like, it's just so beautiful. As
I
in,
got
like,
it.
you only have one of these.
object
Yeah.
and the morphism downstairs into it, and I lift it back to morphism
Yeah,
upstairs.
exactly. There's a unique.
Yeah, right. And that and now you
So
see that
awesome.
this is a discrete off vibration.
This is,
Um,
this is so cool. You know what else is a good example of this? A whole grain Petri net is a graph internal to span, right? And an automorphism is one of these kinds of transformations. It's interesting.
yeah, I really liked this because I had never realized that the proper level of generality for the notion of discrete off vibration is just a map of spans.
Yeah.
The notion
Yeah,
of discrete
that's
off vibration doesn't have anything to do with categories, which
Yeah.
just happens to be the interesting one. But
That's
this is a discrete off vibration of spans.
This
That's
is a cool yoga.
yeah, yeah.
That I have not seen before.
Yeah, and so that tells you in a very ridiculous way what a discrete off vibration of models is.
Yeah, which is really nice because it would not be obvious how to define that if you didn't. This is way nicer than what it would be if you tried to copy, say, the two algebraic definition of discrete off vibration. You know,
Yeah.
using like internal arrow on.
Yeah, yeah,
Really
yeah.
rather nice.
Yeah, and all of this again applies for a Cartesian. So a discrete off a map of Cartesian models is a Cartesian discrete off vibration. If both models are Cartesian, then it's a discrete off vibration, and the map is and the map preserves product.
Is there a nice purely double categorical way to say that left thing is a pullback in the double category of spans?
That's a great question. I mean,
Considering that composition
double
in span is pullback, is given by pullback, like
it's a great
There's
question.
something
There
like-
probably is.
Well, like a characterization of
so I have a generic
cell.
now if I have I have a square in a double category,
Yeah.
right? Is there an abstract way of saying this is one of those guys
right.
that only uses double category foo?
Right, what properties does
Yeah. And there's something to note here, which is that like we're taking this
Mhm.
and we're considering we're taking like like not a companion, or maybe a companion. You can take a companion.
When did I?
of this particular morphism?
Yeah, we
Yeah,
can take a companion of this,
yeah.
which considers it as a span.
Sure. Okay.
Up to XD, yeah, into XD, right?
Mm-hmm.
And the pullback, did I do that right? The composite of that morphism with the bottom one. So if I crack it up
Oh, okay,
here,
sorry, yeah.
that's the right way to put it.
Oh, companion? Oh, right,
Yeah,
right.
yeah. Put the companion here.
Mm-hmm.
And yeah, this bottom composite has at its apex this KM.
Right, and the span.
So now I think what you want is that this is an isomorphism.
Which is an oh,
Yeah,
this thing
this
here.
is an isomorphism. That's it. That should do it.
Uh,
That should do it and nothing more.
Well,
So
surely not
you
KD to
take
XD.
the companion,
That goes
okay.
forward.
Take the companion, you
Uh-huh.
put the companion square as you have. Right,
Mhm.
I think this will work. Now we have, as you've shown, we have a canonical map here. From this one to this one,
Mhm.
what that canonical map is, right? It's KM mapping into KM, mapping into the pullback, it's the gap map. It's KM mapping into the pullback of this wedge. Right?
I'm still having trouble catching. I lost track of what was getting drawn somewhere. I'm sure you're right, but it looks like you keep just pointing at.
Like,
Okay,
Right,
yeah,
right.
yeah.
you're writing the whole
Yeah,
thing
yeah,
out,
yeah.
right?
Sorry, this
So
is-
we don't know that this is a pullback yet.
Okay,
yeah.
we want to prove
But
it.
now, what we know is that the bottom composite here,
Uh-huh.
right?
But
That is the pullback.
Yeah,
That
yeah.
that's
Oh,
the
yeah,
pullback.
yeah.
That's-
Right. You're saying
And this is the
yeah.
canonical map, the induced map on the composite here, into
Right,
the
right,
composite there
right,
is the
right, right.
canonical.
That's
map
it. Yeah, I'm
with
with
the
you
pullback,
now.
the gap.
Mhm.
right.
Mhm.
And so we just asked
If
that
that's
be an
invertible.
isomorphism.
Yeah. So right. So
that's what the condition
the
is.
condition is that you have a cell, and if you take the companion of its left side then and
It becomes
compose
an
it,
isomorphism.
then it.
Yeah, so you
Yeah.
can, you might
Yeah,
be able
so-
to, that might be the generality that which you do
Yeah,
this into
like,
any
yeah,
double
have
category.
companion
You
to-
say as long as you have companions, then
Uh-huh,
you can do it.
Yeah. So there was another idea Evan had, which was to use tabulators. But and there's something nice there. But yeah, I'm kind of down on tabulators lately. They're scary. So yeah, I like companion seems lighter than tabulators to me. I like
Companions
the
are very light.
yeah.
And this comes up with like so many of the things, like, you know, the idea that this is not, it's almost like saying that this is a commuter transformation,
Yeah.
but it's not, because that requires you to also take the other side
Hmm.
and put
Right.
it up here.
Right.
So it's like half a commuter transformation.
Does it
Uh,
does surely
those show up.
this is surely false, but being a commuter isn't saying that like both squares are pullbacks or something, right? I mean,
I actually don't know what
in
happens.
in the
I
case of
really
span,
don't
I
know what
wonder
happens.
I wonder
I actually I should know this, but like what it means is that you also put this up here.
yeah.
So you also take the companion here. Oh, that may not be a difference. There may not be a difference.
Maybe there's just a commuter.
Maybe it is a commuter transformation.
Okay.
Which would make me very happy.
That would be
because
cute.
commuter transformations like are
Very
super
normal
tied
and
into-
friendly and
Well, we have just
everywhere.
work on a symmetric monoidal, a pseudo functor that is lax monoidal from span into quintet
Mhm,
of cat.
mhm.
But where the lax monoidal structure is commuter, then that's actually that's the Frobenius condition
Mhm.
considered. Like it being a pseudo functor from span makes it Bechdel-Valais, and then the commuter condition encodes Frobenius,
Yeah.
which is somehow like I don't know. It's less somehow off kilter in a way. I don't know. I like commuter transformations. They show up all the time. Like
Yeah.
there's a fun thing, which is that if you know that this is a commuter transformation, and you could like maybe post compose by something from span into quintet, and you can find yourself getting, which is the notion of predicate, and you find yourself getting a notion of predicate adapted to these models under double theory. You get like a model in quintet cat, just something like
Yeah.
a lax model.
Sick.
Weird. I don't know. It makes me happy that this is not a double. It just makes me happy that I've seen this.
Yeah. That's
Like I spend a lot of time
We're-
getting into these computer transformations.
right.
And to say-
Yeah,
to
well,
say
we use
that
them in
this
the other
model-
paper too.
The
Yeah.
map of models is which is a type transformation,
Yeah.
right?
Uh-huh.
That is a discrete up vibration precisely when it's a commuter transformation. I think that's cool.
Hmm.
Yeah.
I wanted to make our video rated R, but I
So like I could put a pullback here, and that would be discrete vibration, presumably.
that would be
Hopefully that's the
if you just switch it, that's a
Yeah.
discrete vibration. So hopefully that's a conjointer.
Yeah, hopefully that's
Is there a word for that? Conjointer?
Conjoint, well, the commuter.
Oh,
doesn't
commuter,
tell you
yeah,
which
yeah,
one
yeah.
It is, so conjoint commuter.
Yeah, someone sometime called what we're saying commuter. Someone called them companionable sometimes, right?
Yeah.
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 If you needed to use the two sides, yeah. And the second
Do the
Right.
second one. I think it is true that if you.
I can,
you-
like,
you
do
take
that.
this and you pull it this way.
Which-
Yeah, you take this and you move it down this way. and
Okay.
you're taking the pullback there. And then I think that the truth is that you could just put this in this way because it just doesn't sort of affect it because you end up post-composing and you don't take any more pullbacks. I think that's what it is.
Okay.
That makes me so happy.
And there's a factorization system. That's the last thing I wrote while you were.
Oh. Ta-da.
Ooh. Okay, well, you want to tell us about that?
Comprehensive.
There's kind of not much to like. It's just by local. I mean, the categories of models are
You're
locally
just saying,
presentable.
like, I take any map here and I can factor it through because of this pullback condition here. Or no?
Not well, not that the construction is not like do all those pullbacks one at a time.
No, okay.
Yeah, the construction is like use that the categories of models are locally presentable and lift the factorization system up from like many copies of the category span. The construct, yeah, I don't have a very explicit version of the construction so far, but I think it's always I think you have to expect it to be a little bit complicated because you imagine even in the case of the D+1,
Yeah.
you're already
it's
pushing things
complicated.
around. Yeah, there's already some
It is.
non-trivial co-limits happening.
Yeah.
So you don't just
And
like
initial functors are not like
Yeah.
a terribly easy
Mhm.
concepts or whatever.
Right. So this gives you a notion of initial morphism of any kind of model, including the Cartesian kind.
And so you can do your diagrammatic equations point of view, but now within any double theory.
Yeah, and in
That
a
is useful.
yeah, well, it is actually a slightly narrower scope than our previous paper with Tim and Evan and James Fairbanks, which covered any presentable two category, but using the representable discrete off vibrations. Now, models of two categories of models of double theories is a somewhat narrower class than everything presentable. They're finitely presentable really nice things, but we now get a more native notion of initial morphism. So you can now have initial morphism. You can now have like the map from n dots into a walking n- ary arrow for multi-categories. That's now an initial morphism.
Sorry.
If you have n
dots.
if you include the domains into a walking multimorphism,
Yeah.
that's now an initial multifunctor in this sense.
Sweet. And that's the kind of thing you want. for
And that's
your
probably the
solution
right,
of your- Because you, in the diagrammatic equations thing, you really did want to work with something like multi-categories or symmetric multi-categories, so you have multi-area functions.
Yeah.
Taking part in the equation,
Yeah.
right?
Yeah.
And then so that being initial is part of what you needed in that idea of solving.
Yeah, when you have the wedge product in your it's happening in your equation, and you're like, okay, I've like chosen two elements of the domains of my wedge product, then I need to get an element of the codomain, and that's a binary discrete off vibration.
Cool.
So it seems
Cool.
good for that.
Right.
Beautiful.
Right. So like what you're saying is that, I mean, these are discrete up vibrations because like it's a good name for that because if you take like D to be the point again and you're looking in span set, then this just goes from Coprey sheaves into categories over some fixed category.
And fixed category X.
Right.
Yeah, and it'll land on precisely the
And having this property is discrete up vibrations. And are there other like and so for any, if you take span E or something, then you get, discrete up vibrations, internal discrete up vibrations, or
Yeah. So since this is just a pullbacky thing, I guess without even worrying about this companion thing, if you just take span E, and that's going to be we didn't do anything involving span.
Yeah. I mean, like, I mean, you still don't get it. Just knowing this, you don't get it because like still you needed to do something special about knowing that maps from one were in fact things over, and that's not a companion thing because it uses the factorization system of span that every loose morphism is in fact. This is maybe where Evan was getting at with the tabulator stuff, because like you do need to know somehow like it is not.
I mean, but right, that was
is
talking about span.
It is the tabulator of the loose morphism, right?
Yeah.
The tabulator. So I think this is the But if you go span E, everything seems pretty.
Yeah.
I mean,
What I think right. So what I think Evan's tabulator condition was just exactly that the tabulator of M is a pullback in the type category of your codomain of KD and the tabulator. The tabulator of KM is that pullback.
Yeah.
So that gets you out of being spanny style, but doesn't get you out of pullback. So then the companionable idea might let you, I mean, yeah, get places where pullback is not actually the right condition.
Well, it's the nice thing about the companionable one is it tells you what this it gives you a notion of discrete out vibration. It would give you a notion of sort of quote unquote discrete out vibration for any target double category basically that has that has companions, which is pretty common. Whereas I guess it's slightly more hard to get good tabulators.
Yeah, but what you tabulators and pullback. So basically the Evans idea is more or less for a finitely complete codomain.
Yeah. The you play too hard around tabulators and pullbacks and you end up just saying you embed into a span.
Right.
So
Like
it's
the Lambert.
But on the other hand, I doubt you'd be able to show the equivalence you show without a lot of that structure.
Yeah. Yeah.
It kind of feels like some
getting into tabulators. Yeah, you would. I'm pretty sure the proof will go through fine for span E.
Yeah.
but beyond that, beyond that, things might start to get hairy.
Yeah, no, I mean, there's nothing you used about set here. You only used it pullback condition.
And yeah, that's basically most of the paper. We got
That's really sweet.
The highlights down. Anything else for the?
No, I think
machine?
probably that was quite a long.
Yeah,
no,
no,
that's really interesting.
Yeah.
I'd be quite interested to look at what the corresponding notion of initial functors are in like some familiar settings.
Yeah. So I mean, you can kind of work them out by saying there's a generating initial morphism for every pro arrow that basically takes the model freely generated by an element at the domain of the pro arrow and freely adjoins an element at the pro arrow itself. So for I don't know how
you
to
might
break
have
this on again.
disconnected, but you can this.
So other than initial functors of categories, there's similarly for loose, there's a generated initial morphism, which is you take an object at the domain and include it into the walking heteromorphism. So that's crossing thing. So that's what I mean to say. This is the generated initial morphism corresponding to L in loose.
Right.
And so in a general theory, if you have type morphisms in your theory, this is really saying you have some object D in your theory, and there's a free model on the 1-point set at D.
Sorry, a free model on the 1-point set
at object D. So there's a left adjoint to evaluation at D from models to set.
Right. Okay.
And so
right.
And then there's a left adjoint to evaluation at M from models to span. So at D takes D models. I shouldn't really use that notation because that makes it look like I'm talking about D modules, and that's the set. So there's a left adjoint free at D, and similarly, evaluation at M takes D models to span the category whose objects are span, and that has a left adjoint too. And those are the generating initial morphisms.
Right.
So that gives you a little idea. Yeah. So we don't have a good description of like of a formula in terms of like connected components for detecting initial morphisms. Yeah,
Right.
Chris Brown is working on some related stuff right now, mainly in code. But yeah, but you don't have the whole like package of comprehensive factorization system where you can be like, there's a notion of limits such that restricting along initial morphisms is the same as preserving the taking of
Right.
limits, and that you can compute from a given a morphism of models. It's hard to tell in a general theory right now when it's initial. But you at least can, that at least lets you, like in any particular case, you can probably compute those and see what some examples look like. In the paper, I show like the most interesting one for the theory of a natural transformation, which gets like a little bit funny. And so you can, that's at least something.
Okay. Cool.
Yeah.
Okay.
Thanks, guys.
Yeah.
Sweet.